using lever-powered upper arm systems and pumping away, and we were able to back calculate what this power output was and the force and hand speed. So just from conservation of power, we could figure out how fast should the chair be able to roll, by back solving for this velocity, given different resistances, rolling resistance and climbing angle. And so this gives you kind of a speed map of how fast you should be able to go. This is pretty encouraging. 2 meters per second is 5 miles an hour. That's cruising. That's pretty fast. And that would be on flat ground and concrete, or pavement. So did that. We also looked at it in the case where you have to just bench press your way out of trouble. Say you're going over a steep hill or going over stand. How much force could you get out of your hands in a pushing force? And it turns out the Air Force has measured that for control sticks, right? For pilots being able to push on a control stick. So we got, a nice measure of that for the 50th percentile male. And so this, the reason I'm showing you this analysis is this is very akin to what, I think you'll be doing in your papers. Right? It's not crazy complicated, but it really showed us, what's going on with the problem. So then we did some optimization of looking at this velocity map that we should be able to go theoretically. And this is independent of the drivetrain geometry. This is just conservation of power, right? And we know our hand speed. And then we can look at what sort of terrains might you encounter in the developing world, both from rolling resistance. So this would be really hard pavement up to sand or snow or dirt or mud. And then, up to steep angles. We could look at what sort of bike parts are actually available throughout the developing world. And there's different sizes of chain rings and freewheels. And then we had to look at the size of people and how far could they grab up and down the levers. And so you put all that together, and you can see that you can find that if you want to pump away at your peak efficiency for a long period of time, a lever length of 20 to 60 centimeters enables you to do that on the common types of terrains that you would see. So up to about 10% grade and up to gravel, right? Smooth, linoleum up to gravel. So, that means that most of the time that lever range is going to work for you, and you can operate at your peak efficiency. And then when the going gets tougher, what we're able to show is that with that peak force output, when you have to bench press your way out of trouble, you can get enough mechanical advantage with that same lever range to go through much, much more restrictive terrain, all the way up to sand and snow and steeper hills. So the punchline here is that through this analysis, we were able to see that one size of levers would enable you to both operate at high efficiency and operate at high torque when you needed it, right? So this was very encouraging. And I just want to touch on why did we use bike parts again? And I brought I brought a couple hubs here. If you want to look at these, you pass these around, and there's a bike hub in this wheel. But this picture really kind of sums it up. Out in the middle of nowhere, you will always find these guys working on these type of bikes. And what's great about these type of bikes is they haven't changed for over 100 years, right? No joke. It's crazy. But, same single speed, same, freewheel, same type of chain ring, even same couplings, same, mustache handlebar. Look at this, linkage brakes. These don't even have cable brakes. You can find these bikes all over the world, any sort of village. And I think Hero Cycles, which is the biggest bicycle maker in the world, makes 75,000 bicycles a day. Right? There's a lot of these parts all over the place. And so, you're holding a front wheel right there of an LFC, and you can see there's a bike hub molded right into it, or it's actually pressed into it. But that other wheel has one molded into it. So you can see different ways that we could manufacture it. So that's why bike parts have been great. Okay, so now back to the story of how this thing actually came to be. I had done all this analysis, right, as an independent study as a grad student during the spring of 2008. And this was the first rendering of how we thought the wheelchair could work, right? And the idea was that when you wanted to use the levers, you go into this orientation where it lowered your center of gravity, right? So you were stable. You'd have the big wheels in front so you could climb over obstacles. And then somehow, clearly missing, right, you could flip the seat around and turn it into a regular wheelchair. And we won the ideas competition with this, Because we presented the analysis and we actually made a prototype of one of these levers. You can see the lever here is at the center of the wheel. Our current ones are not. They're forward, which is for a good reason. But I think this is cool because you can see how rudimentary it was to start, but we got money for it, right? And we got to develop it further. And we made some prototypes. Here's a first prototype that we made with some wheelchair makers from Zambia who happened to be at MIT during the summer. Made with them is an overstatement. They gave us some good feedback and tried it out and did some prototyping with us. But we rode around campus. This is a very MIT-esque picture, right? In front of the thing and looking proud and feeling good. And then we made a version for our Tanzania, Kenya, and Vietnam. We made 3 of these first prototypes in the summer of 2008 using our Ideas Competition funding. We made them in wheelchair workshops in those countries. We tested them with people from those countries, and the consensus was, it was awful. Like, just awful, totally terrible. And so this was not in the paper, right? But this is good for you guys to see. And I'm fine talking about it because we learned a lot from this. And so, this was such a classic example of we had done our analysis like good engineers. We had ridden our prototype around campus. We were like, wow, we can go up steep hills. This is so cool. And then we made this prototype that had like an adjustable seat. It had some brakes. This thing weighed over 100 pounds. And it was really hard to get into. Like, we had a guy, a wheelchair user get into it. He was like, it took him like 10 minutes. Like, and it's kind of sharp and dangerous. And they were like, this is crazy. This thing is really dangerous when you go downhill. I don't know if you can tell here, but the back wheel is actually tipped backwards a little bit. So the rear wheel tries to always center. Otherwise, when you go downhill, most of your rolling resistance is happening at these big front tires, right? But your center of gravity is behind them. So what happens is if you deviate at all, you get a force couple that wants to flip you right around. So this flipped around really quickly. When we climbed uphill, what would happen is as you go uphill, you load the rear wheel more and more, and you reduce the load on the front wheels. So this would sink into the ground, and then these would lose traction. Right? So this thing was awful. And on top of that, you can see the pivot of the lever was right there, but you could only grab the levers like right here, right? So we weren't, we were getting not even a 2-to-1 change in mechanical advantage. So it didn't even work to the analysis. So yeah, total failure, but it forced us back to the drawing board. And I think the real lesson to learn here is that we failed relatively quickly and early, and we're able to iterate to correct it. So then we came back to MIT, and we were like, why are we trying to switch the seat around and do all this funky stuff? Why not just put it in a regular wheelchair platform, and and then you can take the levers off and it's a regular wheelchair. And at this point, we made this guy, which is like, this thing looks like a total piece of junk, but it was really functional. Unfortunately, we've lost one of the levers. But I rode this all over campus, up and down the Charles, really got a good sense of it. I stole this seat out of my mom's workplace lunchroom because it had a metal frame underneath that we could weld to. But we learned a lot by this, and we were able to actually test it and collect data, and that's what we used to write that first paper. But can anybody guess where the biggest loads are in this chair? Here, I'll pick it up. This thing weighs a ton too. It weighs like 60 pounds or more. All right, so you can see it. There we go. Didn't get a tire in the face. So where do you think the biggest loads are in this thing? The axle? That's a good guess. But the biggest static forces. And it's actually in the chains, right? Because you look at the length of this. Remember, these are made from bicycle chain rings, which usually would have your pedal mounted right here. And then all of a sudden we put this massive lever length on, right? And so as you increase this length, you have to balance the moment generated about the axle. So, the force times this distance has to be balanced by the force in the chain by just the radius of the chain ring. So huge loads in the chain. And what we learned the hard way is that we would flex the hell out of the frame and the chains would fall off. Initially this design only had this cross beam here and that cross beam here, but this thing was so flexible the chains would fall off, so we had to put these stiffeners in. So, it was a good example of kind of learning things the hard way, but then it made us think about like, oh, what's actually going on in here. And stiffening the frame has always been like a big priority, even now in the current chairs that we have. Okay, so that was this chair. Ugh. I'm bummed we lost the other lever. We also bent him. You can see that.
On purpose?
Not really. I'm taller and stronger than most of the clients. So if I put it up against the wall and really reef on it, yeah, I can bend them. Where's my clicker? There it is. Okay, so that was the first prototype. And, why do you think we use 3 wheels? This is a good mechanical question. Any ideas? You don't usually see 3-wheeled wheelchairs, right? You usually see 4-wheeled. Yeah?
It's not always going to move around, so you can't afford it.
Exactly. Yeah. So, it's like the milk stool effect. Like you have a 3-legged milk stool, it doesn't matter how rough the ground is you put it on, 3 points of contact to find a plane, they will always be in contact with the ground. 4 points, you can have one off the ground a little bit, and that's like having a table, a 4-legged table with a short leg. It rocks back and forth. The other reason we did it is we could use a much bigger front wheel than a regular wheelchair would have that has 4 wheels. Because with a 4-wheel chair, you're usually putting the wheels right around the footrests. Like a hospital chair has a footrest in front of them. Some wheelchairs have the footrest behind them. But you're limited because the wheel could hit the footrest. So by having the 3-wheel design, we could put it way out front and use a much bigger front wheel, and that's great for going over obstacles, right? Bigger diameter wheel, you can roll over a bigger obstacle. And another lesson here is we stole this idea from somebody else. This is another chair on the market, the Motivation 3-wheeler. It's a great chair, and we use the same diameter as their wheel. We've redesigned it a bit, but it was a good idea, and so we copied it.
Did people complain that the wheel was too far out? Like if you're moving it around the house, I think that works into
Yes and no. So it's a bit of an optical illusion how long this thing looks. This is the Indian version that's in production, and it's about a 1/2 inch longer than a standard hospital chair. Because a hospital chair has your footrests sticking out front, and those stick out way farther. But just because of how the chair is proportioned, it doesn't look as long as ours. Now that said, when you try to like get up to a cabinet or something, that the front beam can hit, and so that can make the reach a little bit hard. But the feedback hasn't been harsh enough to warrant changing it. The off-road capability, and how it can travel supersedes it. Okay, so at this point, we wanted to get more feedback from the field. We had learned good lessons in Africa and in Vietnam, and this was the period in the project where we went into 3, I would say, kind of legit field trials, where we went there, tested the chair, and then went back and got follow-up data. So we did it first in East Africa, in Kenya, Tanzania, and Uganda, and then went to Guatemala, and then went to India. So we built the blue chairs in East Africa. We built these in Nairobi, and we gave 6 of them out, and we made 2 more, one for ourselves, one for our partner. But like one of the critical engineering things was figuring out the structural loads, right? And where do you think a region of this chair that could be a little dicey is structurally? I told you about stiffening up the levers, the lever pivots, and I'll show you that. I'll put this up on the table. This one's even heavier. Ugh. Okay, so you can see underneath, stiffener right here for the lever pivots. That was pretty important. But what other structural load do you think could be an issue? Yeah. Yeah, it's pretty short. There's not huge loads going through that.
So you're pushing your back is
we are a little concerned about that, and I'll talk about that actually with the next one. But this is a heavy gauge steel, and it's a very short cantilever length. But yeah, the front beam. And that comes into kind of the next engineering toolbox thing I wanted to talk about. Oh, I should take this down so you guys can see the board. But I'll put it back up in a minute. So going into quals, how many of you are thinking of taking quals, by the way? Just one? Come on. Okay. Going into life, you should know this stuff. So your next engineering toolbox thing that I think is really important is being able to do free body diagrams and structural calculations, right? And so, we could take the wheelchair, it's got the 3 wheels, and we could do, figure out where the center of gravity is, or you could just put a scale under the 3 wheels, and then you have this front beam sticking out that comes out to the front wheel. Okay, so you can work that out, and then you have this situation where you have your front beam of some length L. It's got some force from the front wheel acting on it of F, right? And then it's reacted back against the frame. So it's in a cantilevered situation. So one thing you guys should be able to do is do a free body diagram and then a shear and moment diagram, right? And so this one's pretty easy to think about intuitively. And this moment has to be reacting against that force. So you have M, and there you go. There's your whole free body diagram. And so then you can draw a shear, and you guys have done shear and moment diagrams, right? But this is something you should go back to and think about, like look at life in the sense of shear and moment diagrams, right? We do a great example in 007, the undergrad class I teach in the spring, where we look at the Tower Bridge in London. So go home and look at that and think about why the supports of the decks are designed the way they are. Typically, suspension bridges just have a big cable that has vertical cables coming down to support the decks. The London Bridge, the Tower Bridge, has a big beam that supports the cables that hold up the deck. So you should think about why. And if you do a free body diagram, you'll figure it out. So anyway, moment conventions for shear is that counterclockwise or clockwise is positive. And so we've got a counterclockwise shear. And so that's negative, so we have negative F. And then conventions for moments is that if the beam smiles, it's a positive moment. This is plus shear, this is plus moment. And so we've got a positive moment. That moment is F times L, and it goes down to 0, right? So here's your moment. This is plus FL, right? And if you want to ever check yourself, the derivative of the moment in terms of X should be your shear. So we've got a negative moment, or negative slope, negative shear. We're all set. Cool? All right, you guys should be able to do that. Now, the next thing you should be able to do is figure out, how is this going to affect the strength and stiffness of the structure, right? So when you have a beam and bending, your bending stress is an equation you guys should go to sleep every night dreaming about because it's so important. Negative my over I. And this is such a simple equation, but there's so much easy fundamental stuff going on here. And it all revolves around this, your moment of inertia, right? So your moment of inertia is the integral of y squared dA. Now, have you guys put a lot of thought into what that means? Physically. I think of it in terms of leverage, right? Because you have, let's say we take the cross section of a beam, right? So here's the beam, and there's a moment being applied to it like that. And we have our neutral axis right here, right? And we have, this is our direction of y, which is this. And here's a little differential element, dA. What moment of inertia does for you is it gives the material more leverage to counteract this moment. So say right here, this material has a yield stress of sigma y. If we move that little differential element up, it can make a bigger moment, right? And look how this sucker scales, right? It's y squared dA. So if you increase this height, you get big returns on that investment. So if we look at just some cross sections, sorry I'm going right to left, but if we look at some cross sections, this is height, this is base, and this is all stuff that, you know, just have in your back pocket, because you can look at so much stuff in the real world and be able to figure out very quickly what's going on, why it's designed the way it is, why it might be strong or weak. I live in Somerville, and every morning I drive over the bridge that goes over the commuter rail tracks, and it's like rusting, and the big I-beams at the bottom are like starting to buckle. And I'm like, this is dicey, you know, they're rebuilding the bridge, but I know that because I think about moment of inertia. So I for a rectangle is 1/12 BH cubed, and I for a circle is pi r to the 4th over 4, right? In parallel axis theorem is that I total is I inner minus I outer. Say you have a hollow cross section. You can figure out what the I inner here is and the I outer from these overall dimensions and figure out your overall I. Okay, so going back to this, right, let's look at how that scales. Where, you know, we have sigma equals negative my over I. Where's our max stress going to be? At the extreme, yes. So sigma max is going to be at negative my max over I, right? And this for a cross-sectional thing of H and B, a rectangle. So that's going to be H over 2I. And then how does H scale for a rectangle? This is 1/12 BH cubed. So our stress is going to be proportional, right, to 1 over H squared for a rectangle. That's pretty cool, because small changes in height will give you big reductions in stress, right? That's really, really powerful. So going back to this, I don't have to lift it up for you to see this. Why might we have chosen this cross section? Yeah, we got much bigger moments going this way than this way, right? So why not take a big height here and a smaller height here, so we can make a relatively light cross section but still get a lot of bending resistance, right? That's why we designed this. And we actually went so far as to look at common steel sizes in developing countries. And these are in millimeters, but 24 by 50 by 25 by 1.2 is what's used in this one, in this one. This one's the 1.5, and that's why it's a bit too heavy. But with the 1.2 millimeter wall thickness, we could have a factor of safety of 6 relative to static loads in the chair. So that means you can sit over 1,000 pounds in the seat of this chair and it won't bend. And a factor of safety of like 6 or 7 is pretty good for something that could really injure somebody if it broke, right? Elevators have up to about 11. Bicycle frames are about the same as these, like 6 or 7. You know, you can get some crazy BMX videos of guys jumping off like 6-foot high, like retaining walls and landing and not breaking the frame. Like, figure out the loading in that situation. You're going to see, you know, if you look at the deflection of their legs and figure out, you know, if it's a constant acceleration, what the loading should be, it's going to be about 6 or 7. So we had to make the chair really strong. Okay, then the other thing I wanted to mention is stiffness. So we go back to this example where we have a beam, we have F here, we have the length. And when we apply this load, the beam's going to bend a little bit by some delta, right? And another equation you should have in your back pocket all the time is deflection of beams, cantilever beams. So, or any beams will follow this same type of format. But your deflection is FL cubed over 3 EI. And so if we want to figure out the stiffness here, right, that's just F over delta, right? And so, or sorry, it's F over delta. And so that is 3EI over L cubed, right? So again, look at the scaling here of what's going on. This is your bending stiffness. And it's the product of E and I. And remember, I is proportional for a rectangle, is proportional to h cubed, right? For a rectangle. So, if you wanted to make something a lot stiffer, all you have to do is change the height a little bit and it'll get a lot stiffer, right? For a given material type, right? Or look at how this scales, L cubed. Make it slightly shorter and it'll get a lot stiffer. So you asked about the seat back, right? You know, that short seat back is going to be a lot stiffer because of that difference in length. So these are kind of two principles that you should keep in the back of your head when you're designing stuff, of like, how does stress scale, how does stiffness scale? And one thing that I see all the time, I see it in developing countries, but I also see it here, is that like when people want to make something stronger, they want to add more material. Or they want to use like a higher yield strength material. You know, you can change this too and use a material that can withstand a higher strength. But you don't have to do that. You could change the geometry, right? And that's why we used a rectangular box section or cross section box tubing in the chair. Yeah, so I literally go through my life thinking about this stuff. You know, I look at everything and it gives you a lot of insight into why, like, you know, go into a building and you see an I-beam like this, you can be like, oh yeah, I remember I is the integral of y squared dA. God, look at where they're putting so much dA here, you know? And here's the neutral axis, and look at this y, right? Wow, that makes a lot of sense, why they would make it that way. Pretty cool. Okay, we'll go on with a wheelchair. But that's useful stuff, big time. And I lost my clicker. Oh, there we go. Okay. All right, so back to the stuff. So we tested this chair in the field with these 6 people, and 3 of them were full-time wheelchair users. The other 3 were, 2 were tricycle riders, which we pretty quickly figured out probably weren't our target demographic, because if they could walk short distances or use crutches, a tricycle works really well. Because indoors they're all set, and they can carry more load on a tricycle than a wheelchair. So, our target market for this is really people who would need a wheelchair. So anyway, we had 3 full-time wheelchair users in that trial. The other person couldn't use any type of device alone. She had just such bad muscular issues. So anyway, we did this quick and dirty test. And N is only 3 here, not a lot. But we asked people about how well did the wheelchair do in kind of easy indoor terrains, going to harder and harder terrains all the way to off-road. And we saw this big discrepancy between, like, off-road, this thing seemed like a monster. It did great. But indoors, it was horrible, right? And the moral of the story here again is that because we went back and talked to people, we figured out why. And the big issue, like, look at how big this thing is. You know, look how wide that is. You know, is that it couldn't fit through a standard doorway. And, you know, I'll tell you one more mistake that was made here, and why is, I'm a lot bigger than your average Indian, right, or Guatemalan, but I can fit just fine in this chair, right? This chair was largely designed around me, and I am not a target user, right? Look at these ridiculously long levers. Right? These look comically long. Oops, other side. But if you're my height, it's up to my shoulder, right? So this made sense. But I'm like 7 feet tall from the waist up because I have really short legs. So this made sense for me, and we had to think about, like, oh, people all around the world may not be built like me. But that was one of the reasons we made that mistake and made it too wide. So we figured out that width issue. The next thing was that people felt it was way too high and precarious, that it could tip backwards. And just look at the seat height of this compared to the black one or the red one. It's a lot higher. It's actually 5 inches higher. And so that made it really tippy. And also, picture a person that has a spinal cord injury and doesn't have any control of their abdomen, pushing really hard on the levers. What's going to happen? Won't. Right over the back, right? And that shifts their center of gravity back, they fall over. So, big issue. But we figured it out because we asked people. And that's not something I would have realized, right? Because I have abdominal control. I could clench my ab muscles, and I didn't even think about it when I was pumping the levers. And the third issue was that this thing is a pig as far as weight. This is 65 pounds. Other wheelchairs on the market are closer to 45. So people are like, this is way too heavy. Like when I want to lift it up onto the top of a bus or have somebody else do it, just way too heavy. So that forced us back to the drawing board, and we had to think about how to make the chair narrower and lighter and more stable. And this is another prototype that's not in the paper, but I think it's really great in that it shows like these quick and dirty prototyping skills that we used to come up with better solutions. So one of them was to make it narrower. We figured out this style of armrest where you can see it on both of these chairs. The armrest actually starts on the outside of the seat back frame and tapers in to the front of the seat. And what that does is it follows kind of the tapering from your hips to your legs. And so you can make the chair wide enough at your hips but narrow at the legs, and it leaves room for clearance of the levers. Right? So that was one way we made it narrower. Another one was we put jogs in the levers, which shifted all the drivetrain in and also made it narrower. And we also, if you look at the tire type here, this big, knobby off-road tires, we went to more of a hybrid tire, which is about, I think it's about a 1/4 inch narrower, but that's a 1/2 inch on, overall over the chair. So all that added up made really a narrower chair. And then to reduce weight, if you can see this chair, I don't want to keep lifting this thing up. But if you look at this chair, we had to find ways to tighten the chain. Oops. So if you look at this chair, you see how there's a bolt plate where the wheel and the whole bearing assembly for the axle bolts on, and we could slide that forward and back, right? That is a 1/4 inch thick steel plate on both sides. That is a honking piece of steel. It weighs a ton. And so in the later evolutions, we said, let's not use that much steel. And this one, which is a lot lighter, by the way, this one, you can see, is that going to fit? Yeah, this one has the whole seat subassembly slide on this lower rail. There's a clamp here and clamps in the back, and the chain ring is connected to the seat here, but the freewheel is connected to the lower frame. So just by sliding the seat forward and back, we could tension the chains. And this is much, much, much lighter as a result. So we prototyped that, and then more stable. Can you see the feature that would make this more stable? It's lower. Yeah, you can see it's a lot lower. But what?
Higher back.
Yeah, it's got this thing. Custom made from a t-shirt wrapped around foam, right? Really quick and dirty, but it's this back support. And what these do is act like a bench press bench. When you're pushing really hard, you have these big forces coming in your shoulders that's trying to bend your back backwards, but this supports you right between the shoulder blades, just like a bench press bench does, and prevents your torso from tipping backwards. And we prototyped that all here before we went back in the field. And it doesn't have to look pretty. Ugh. All right, hopefully I don't have to lift this thing anymore. Cool. How are we doing on time? Oh. Not much. Okay, so we came up with these new designs. We tested them in context in the field. This is a rural village in Guatemala. We instrumented people up with biomechanical data acquisition equipment that we designed that can measure their oxygen consumption rate, their power output, how fast they went, and we could test them in the LFC and in the regular wheelchair. This is just a picture of the data acquisition system. If you bought all this stuff off the shelf, it'd be tens of thousands of dollars, and we were cheap at that time, so we built this for a couple grand, just using some SparkFun electronics stack boards and conditioning the signals a little bit. But we could get all this good biomechanical data, and so went back to Guatemala, talked to people using these new chairs, and we reduced the width by 3.5 inches versus the East African chair. We lowered the CG by 5 inches, as I said. And we added this back pad. You can see it in action right here, right? He's not tipping backwards. And we took 20 pounds out of the frame. So we did the biomechanical tests, and we saw that it was, one, a lot faster than regular wheelchairs, about 80% faster, and it was about 60% more efficient in these tests. This was the trial, too, where people had not been trained, and we basically had to throw out all the data because they didn't know how to use the chair when they got into it. You know, we went to do the follow-up testing, and they were like, yeah, I've never actually ridden it. You know, and so the data we were able to collect were from our partners who had been riding it. And these data are really good, but all these guys are basically professional athletes. They're all on the national basketball team for Guatemala, wheelchair basketball. So they're not quite your average user. That's part of why we did the India trial, too. We also asked them the same survey questions, and you know, making the chair narrower and lighter and everything, you know, really upped the indoor mobility. And it was better outdoors. It scored better, but not as drastically as we thought it should. And again, the moral of the story here is we asked why. And why, one of the reasons was people didn't feel secure enough in it. They felt like they could fall out, particularly when going down hills and pulling back on the levers to apply the brakes, which are these little bars right here that protrude